Saturn's iconic ring system is a result of countless icy particles and debris orbiting the planet. The rings are composed mainly of water, ice and dust, ranging in size from tiny grains to larger boulders. The rings are incredibly thin, extending over thousands of kilometers but typically only a few tens of meters thick. The rings are named alphabetically in the order of their discovery, from the main rings designated A, B, and C, to fainter rings like G and E. The prominent Cassini division is a gap between rings A and B, caused by gravitational interactions with Saturn's moon, Mars. The Roche limit explains why Saturn's rings haven't merged into a single moon. Tidal forces prevent larger moonlets from forming within this boundary due to Saturn's gravitational influence. The rings' brilliant appearance is due to sunlight reflecting off their icy surfaces. Some rings have irregular and wavy edges, possibly caused by the gravitational pull of nearby moons. Saturn's rings are not permanent, they are gradually being pulled into Saturn by its gravity, but the process is very slow, taking millions of years. Shepherd moons, like Prometheus and Pandora, shape and maintain the edges of certain rings by exerting gravitational influence. The F ring is particularly dynamic, exhibiting clumps, strands, and kinks due to the presence of shepherd moons and interactions with smaller ring particles. Saturn's rings might provide insights into the early stages of planet formation in our solar system. The ring's water ice could hold clues about the history of water in the outer solar system. Scientists are puzzled by the differences in color and composition among the various ring segments. Some rings, like the A and C rings, contain radial spokes that appear to be caused by electromagnetic interactions with the planet's magnetic field. The ring's particles move at varying speeds, creating a complex interplay between gravitational forces and collisions. The rings can cast shadows on Saturn's surface and each other, creating intricate patterns. The nature of the bright, blue ringlet in the B ring, known as the blue ringlet mystery, is still not fully understood. Saturn's rings are not unique. Other gas giants in the solar system, like Jupiter, Uranus, and Neptune, also possess faint and narrow ring systems. The age of Saturn's rings is debated, with estimates ranging from as young as 10 million years to as old as the planet itself. The Cassini spacecraft provided a wealth of information about Saturn's rings during its mission from 2004 to 2017. The gap between the rings and Saturn's cloud tops is called the Roche division, a zone where tidal forces can influence the movement of ring particles. The ring's particles can collide and stick together, forming larger chunks in a process known as coagulation. Some moons, like Pan, have ridges and shapes that suggest they might have formed from the material of the rings themselves. The dusty A ring is unique as it's primarily composed of tiny ice particles originating from Saturn's moon Enceladus's geysers. The Cassini spacecraft's grand finale provided detailed data on the innermost part of Saturn's rings and their interactions with the planet. Saturn's rings are best observed from Earth during times when they are edge onto the Sun, minimizing glare. The exact mechanism that prevents the ring particles from clumping together to form moonlets or larger objects is still a subject of research. The ring's intricate structure is believed to be influenced by resonances with Saturn's numerous moons. The B ring contains a region known as the Huygens Gap, cleared out by the shepherd moon Prometheus. There is ongoing research into how the rings might be linked to Saturn's overall magnetic field and its interactions with the solar wind. Some gaps in the rings, such as the Encke gap, are kept clear by the gravitational influence of nearby moons. The ring's appearance changes as Saturn orbits the Sun, affecting our perspective from Earth. Saturn's rings are not solid, they are made up of countless individual particles orbiting the planet. The study of Saturn's rings can shed light on how small bodies in the solar system interact and evolve. The ring's composition varies with distance from Saturn, with different bands containing varying proportions of water, ice and rocky material. Saturn's rings likely went through several phases of formation and evolution over the course of billions of years. The ring's brightness can be affected by the angle of sunlight, causing some regions to appear darker than others. The ring's complex patterns are influenced by gravitational resonances, orbital dynamics, and collisions. The unique patterns and interactions observed in the rings might provide insights into how planetary systems form around other stars. The faint, outermost ring, called the Phoebe ring, is associated with the irregular moon Phoebe's orbit. The particles in Saturn's rings range in size from micrometers to a few meters, creating a diverse ecosystem of material. The Keeler gap contains the moon Daphnis, which creates waves in the gap's edges as it orbits within it. The study of Saturn's rings has led to advancements in our understanding of fluid dynamics and particle behavior in space. The influence of Saturn's rings on its magnetosphere affects its interactions with the solar wind and its radiation environment. The ring's intricate patterns have inspired artistic and scientific exploration alike. Some moons, like Atlas, appear to sculpt gaps within the rings through their gravitational effects. The age of the rings might provide clues about the timing of significant events in the early solar system. The mysteries surrounding Saturn's rings continue to captivate scientists and space enthusiasts, driving ongoing research and exploration.